Hey everybody, Dr. A here, and in this video we're going to be exploring an example of how to compute the centroid of an area. So let's go ahead and dive into it. In the given information, we're being asked to compute the x-coordinate, which we call x bar, of the centroid of the shaded area. Now, the shaded area is given by two functions that are bound together. So we have this function y equals x, and we have a second function y equals 1/4 x squared, and the area bound in between those functions is what we're interested in finding the centroid of, okay? Now, because we have an area bounded by two functions that is not a simple shape, of course we have this, parabolic curve right here, then we're going to need to use the integral form of our centroid formula. So under solution, I'm going to write out the integral form of x bar. So we're going to have x bar equals the integral of x tilde dA divided by the integral of dA. That's the basic formula that we are going to end up using here, okay? Now, what we need to do is understand all the components of this integral, right? So the first thing we're going to do is explore this concept of dA, which shows up in both integrals, okay? So dA is going to be an infinitesimal differential slice of this area. So for example, dA is going to be like a slice right here, okay? This will be a little area dA, all right? And I'll put a little note over here, that's dA. Now, what is the width of dA? Well, the width of dA is going to be a little differential dx, okay? And then the next question is, what is the height of dA? What is this height of this differential element? Well, that's going to be something that we can just call maybe delta y, okay? So I can write over here, dA is equal to delta y dx, okay? Now, how can I be a little bit more explicit when it comes to that? Well, what is delta y? Delta y is the difference in height of points on this linear function, that upper function, minus corresponding points on the lower function, on this quadratic function. So basically what we can do is say, hey, delta y is this linear function minus this parabolic function. That'll give us this change in height. And of course, it's changing as we go across this area, or this shaded area. So we can rewrite this as dA is going to be this function, the linear function, which is y equals x minus this quadratic function right here. Use my laser pointer. Minus this quadratic function right here, which is 1/4 x squared, and we'll wrap that up in parentheses. That's that delta y, and then times dx. So that gets us kind of an expression or a formula for that differential element dA. So that takes care of both of these dAs, which is great. Now what we also need to investigate is the limits of this, the bounds, right? So we need to know where we need to take the integral over, from where to where. Well, it looks like, the area, the blue shaded area starts here at the origin, and it extends up to this point here. But what are those points? So I'm going to make a note over here. I'm going to say to determine integration limits, what we do is set the functions equal to each other, okay? And that makes sense. Think about it. This point here and this point here are common points to both of these functions. So if we set the two functions equal to each other, we'll be able to determine these 2 points, which are the integration limits. And again, this first one looks like it's 0, but let's go ahead and confirm that, okay? So I'm going to turn the page here, and I'm going to set these functions equal to one another. So that first function, I'm going to rewrite it here for our purposes, as y equals x. And then the second function was y equals 1/4 x squared, okay? And so I'm going to set them equal. I'm going to say x equals 1/4 x squared. So I'm just saying, you know, this function equals this function. And then I'm going to do a little bit of algebra here. I'm going to do some rearranging, and I can rewrite this as 1/4 x squared minus x equals 0. And then I can factor out an x and get x times the quantity 1/4 x minus 1 equals 0. And so what I'm doing is I'm essentially finding the roots of this expression that I just established, okay? So this is just basic algebra. So these roots are x equals 0 and then x equals 4, all right? And so, again, we've got these roots here, x equals 0, and then this x value is going to be a 4 here. So how about I go ahead and label this right here, x equals 0, and then x equals 4. Now, just for purposes of information, can I go ahead and get this value up here, this y value? Yeah, that's also going to be 4. Why do I know that? Well, you substitute in x equals 4 into either of these equations, and you'll get y equals 4 here. So I've completely defined the parameters of this problem at this point, okay? So now what I can do is I can go back to my x bar relationship, and I can say, okay, I've got this integral of x tilde dA divided by the integral of dA, and I can start writing these integral expressions a little bit more explicitly. So that top integral, that numerator, is going to be the integral from 0 to 4 x tilde, and then what did we say dA was? dA was this expression here, right? So I'm going to say times x minus 1/4 x squared dx, and then all that's divided by the integral from 0 to 4 of dA, which again is just x minus 1/4 x squared dx. Now, what's the last piece of this that I need to figure out that is still a little nebulous at this time? Well, it's this x tilde, okay? What is x tilde? Well, x tilde is a moment arm, okay? Let's write that down. Remember, x tilde is what we sometimes call an area moment arm, okay? So take a look at the background video if you're a little rusty on that. But what x tilde is this dimension from the origin to the centroid of dx. This is x tilde right here, okay? So it's a distance, a horizontal distance from the centroid to the center of dA, okay? Which again, remember, dA has a width dx and a height delta y, okay? So remember, whenever we're calculating the centroid, especially the centroid of an area, what we're doing is we are using this concept of an area moment. It's like we're taking an area and we're thinking of this as kind of abstractly rotating it about an axis, okay? So if you have an area, in this case dA, multiplied by a perpendicular distance, x tilde, then you get an area moment, okay? So the question becomes, what is x tilde? Well, in this case, x tilde is just x, okay? It's just regular x. And again, this is well defined because we have both functions passing through the origin. That's all in quadrant 1. And so, so this x tilde, this moment arm, is going to be just x tilde equals x, okay? So now we can substitute in x right here. So if I rewrite this one more time, and again, I'm kind of writing this out very explicitly for us so we can best understand it. 0 to 4, x times x minus 1/4 x squared dx, and then divided by the integral 0 to 4 x minus 1/4 x squared dx. Now remember, you can't just be canceling stuff willy-nilly, okay? This is two separate integrals that you just divide by each other. So we're going to go ahead and say, let's evaluate these. Now I'm going to use my TI-36X Pro to help me evaluate these. So I'm going to type these integrals into my calculator, integral 0 to 4, and I'm going to do this top integral first. So let's multiply that x into that parentheses, x squared, and then minus 0.25 times x cubed. And for that numerator, I get 5.33, and 333 continuing. And then we're going to say that's divided by, and then I'm going to take another integral, all right, for that denominator, 0 to 4, and then I've got, of course, x minus 0.25 times x squared. And I get this denominator having a value of 2.667. And so if I divide these two, I get x bar is equal to 2. Now, what are the units here? Well, if we go back to the original problem, no units were explicitly given, but we need to think about this with an engineer's mind. What units should all of these things have? Well, these lengths, the x-y axes should have units of length, okay? So we can put a little note here. X has a unit of length, y has a unit of length as well. Okay, that could be feet, meters, inches, whatever. And then of course, this area has units of length squared. Okay, so when I evaluated all of these integrals, let's make some notes here so we understand. The value of x has units of length, and then this function right here, x minus 1/4 x squared, that is also going to be units of length, okay? And this down here also units of length. And then dx, the dx terms carry implicit units of length, okay? And so when I evaluated this, and I got these values, this numerator and this denominator, that numerator is going to have units of length cubed, and then that denominator is going to have units of length squared. And so you get a final value of 2 with units of length, okay? And so your final answer is x bar equals 2, and carrying units, it should have units of length, so that could be inches, millimeters, feet, whatever, okay? You will encounter some problems like this in engineering or in your mathematics studies where the units are not explicitly given because the problem expects you to understand what the units should be in this given context, and this is one of those problems, okay? So that concludes this video. Hopefully you found it helpful. If you did, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.